All right, so this section is all about gas laws. In your exploration of gases lab, you worked with a water bottle, and this example is very similar to what you will be or have done in lab. Here we see we're starting off with a balloon fully inflated at room temperature. If we pour something extremely cold like liquid nitrogen on it, we see that the balloon begins to collapse. If it warms back up, though, the balloon will start to expand again. And so this is one example how we can see that the gases inside of the balloon are reacting to temperature. My question to you is, why does this happen? So let's take a closer look at properties of gases to help us understand why that would happen. Gases have a very unique set of physical properties. One of those is that they are translucent or transparent, meaning we can see through them. They have extremely low density compared to liquids and solids. They're highly compressible, meaning we can squeeze them into much smaller spaces compared to their liquid and solid counterparts. And they can also expand or contract to fill any container of any shape. Kinetic molecular theory says that gases are made of a lot of really tiny atoms or molecules, and those molecules have a lot of space between them, and they're in constant motion as they collide with each other. So gases are consisting of atoms or molecules that are constantly moving through a vast empty space. We know that this is actually true because we can take a liquid water in this example, and heat it up. And as we do that, the water will start to boil. And it looks like the liquid is disappearing, but it's not. It's just moving into the gaseous state. As their gases are moving, they're going to create what's called pressure. And that's a property that you're going to need to understand. This actually correlates to your exploration of gases procedure B that you have done or will be doing in the near future. So pressure is just the force exerted over an area. If we push down on a blown up balloon, the balloon is actually going to push back. And it's because of those gas molecules that are inside. And what they do is they exert a certain pressure over a particular area. So it's actually just force per area. We measure pressure using a barometer. That's an old-fashioned way where we can look at how the air pressure will push mercury up a tube, and that will help us measure the air pressure in a room. Units that we use include atmospheres, millimeters mercury, harkening back to the barometer, torr, kilopascals, inches mercury, or pounds per square inch, also called PSIs. In this class, we use primarily atmospheres, or the ATM abbreviation. Volume is the amount of space that something takes up, and we abbreviate that with a capital V. We measure that in the liquid form using a graduated cylinder. Solids, we measure volume by taking the dimensions of an object and multiplying them. For gases, we can do the same thing. We take dimensions of a container to see how much space those gases are taking up. Units we use for volume are liters or milliliters. Temperature just measures how fast certain molecules are moving. If we have increased motion, that means that we have a higher temperature. We measure it using a thermometer or a temperature probe. The units that we use in our country for the layperson are degrees Fahrenheit. However, when we're in lab, we use the standard scientific units, which is degrees Celsius. For calculations using gas laws, we want to use Kelvin so that we eliminate the problem of having negative numbers. Standard temperature and pressure is a standard value that we use to measure different properties of gases. Temperature, we typically measure our gases at 0 degrees Celsius, which when we convert that to Kelvin is 273 Kelvin. For pressure, we use standard room pressure of 1 atmosphere, which can be converted to 760 millimeters mercury. So standard temperature and pressure are those two values. If you're ever told you have something at STP, or standard temperature and pressure, that just means that the temperature is 273 Kelvin and the pressure is 1 atmosphere. If we look at the relationship between pressure, volume, and temperature in certain gases, we can see that gas pressure is increased whenever we have more frequent or more energetic or harder collisions. So if we have less frequent impacts or less frequent collisions, that means we have a lower pressure. It's lower force per area. Once we have more gases in an area, then we're going to have a higher pressure. So if we're looking at a relationship that we can quantify between pressure, volume, and temperature, we can look at these three situations. The first one shows us increasing our molecules will increase pressure. The middle situation shows decreasing volume will increase pressure. And the last one shows that increasing temperature will increase pressure. To quantify that, we use a couple of gas laws, Boyle's law and Charles's law. Boyle's law applies to measure changes in pressure and volume where we hold temperature constant. Charles's law applies when pressure is constant but volume and temperature are changing. We can take those two laws and combine them to what's called the combined gas law, where we have the initial pressure and volume divided by temperature is equal to the final pressure and volume divided by temperature. Now this only works when we're working with a particular sample of gas where the numbers of molecules are not changing. Combined gas law requires constant moles. Now, if the number of moles is not constant, then we would have to use a different gas law called the ideal gas law. You, in this class, do not have to be able to do those calculations, but you do need to understand combined gas law and apply it appropriately. Diffusion of gases. Right now in the class, you probably don't realize that I have a vinegar beaker that's open. We're going to mark who smells it first. And we're going to talk about why do the people in the back of the room not smell the vinegar right away? If gases are moving so quickly, why doesn't the smell travel across the room just as quickly? The answer is we have too many air molecules in between. In between the vinegar and your nose, there are millions and billions of air particles. And the typical air molecule has to collide 140,000 times in order to move forward a simple centimeter. So the reason why gases don't diffuse very quickly is they have to move through several other gas particles. Vinegar molecules have to move through those air molecules to reach your nose. Collisions with the air molecules in between are keeping the vinegar from reaching you directly. So diffusion is a very slow spread of one type of molecule within another type.